Hello, and welcome to this tutorial for BioXTAS RAW. In this tutorial, we will learn how to use evolving factor analysis, or EFA, to deconvolve overlapping peaks in SEC-SAXS elution profiles. In order to do this tutorial, you need the raw tutorial data, which is available on the raw website. This tutorial also assumes that you already know how to do basic processing for SEC-SAXS data, such as loading and subtracting the datasets in raw. If you don't know how to do that, please do that tutorial first. Sometimes SEC fails to fully separate out different species, and you end up with overlapping peaks in your SEC-SAXS curves. It is possible to apply advanced mathematical techniques to determine if there are multiple species of macromolecule in a SEC-SAXS peak, and then to attempt to extract out scattering profiles for each component in the overlapping peak. Singular value decomposition, also known as SVD, can be used to help determine how many distinct scatterers are in a SEC-SAXS peak. Evolving factor analysis, also known as EFA, is an extension of SVD that can extract individual components from overlapping SEC-SAXS peaks. So to do this tutorial, we're going to use the data in the SecData folder. In particular, we're going to use this phenylalanine hydroxylase data, PHEHC_SEC. This HDF55 is just the standard raw series save file, so we can open it either by double-clicking or by selecting it and clicking plot. And you can see it's now plotted up here. In order to get started, we need to open the EFA window. To do that, right-click on the item in the series plot and select EFA. So when the EFA window opens, the first screen you'll see is this screen. This shows you the singular value decomposition of the dataset range that you have selected in the plot here. So for evolving factor analysis for EFA, I recommend you use subtracted data. It can be challenging to deconvolve unsubtracted data because it's hard to fit that buffer component properly. And it's almost impossible to deconvolve baseline corrected data because the baseline correction introduces correlations in the dataset at all Q, and that throws off the evolving factor analysis algorithm. So when we open this up, we may want to adjust the range of frames used. In this case, we're not going to do that. The next thing we want to do is we want to look at these two plots here on the right. So the top plot is showing us the intensity of the singular values. And what we're looking for here is how many of these singular values are above this baseline level for the singular value. In this case, it's very clearly 3. This tells us that there are most likely 3 significant scattering components in the selected range of our data set. We can verify that by looking at the bottom plot, which is the autocorrelation plot of the left and right singular vectors. So these singular vectors essentially correspond to either scattering profiles or concentration profiles for the components in the solution, depending on if you're looking at the left or the right vectors. It's not quite what they are, but it's enough to think about it. And so when we're looking at the autocorrelation, what we're looking at is we take one of these singular vectors, we shift it by a point, and we compare it to itself. And the question we're asking is, how similar is this vector to itself if we shift it by a point? If it represents something real in solution, some kind of scattering component, we expect the scattering profile or the concentration profile to be smoothly varying and not changing very much as you move just from one adjacent Q point to the next, for example. And so in this case, we expect it to have a relatively high autocorrelation, near 1. If instead the component essentially corresponds to noise in solution, then when you shift it, it'll be essentially completely different from itself, and it should have a very low autocorrelation, near 0. In this case, we again see 3 strong autocorrelations, near 1, which confirms the idea that we have 3 strong scattering components in this solution. My usual cutoff for strong is about 0.6, 0.7. Once we've determined how many singular values we have, how many strong singular values corresponding to how many strong scattering components, we need to set that number here in the input. Raw tries to guess this automatically. You can see in this case it did a good job. It doesn't always do a good job, and in particular if you change the range of the intensity that you're using, you will likely have to adjust the number of significant singular values. Once we've done that, we hit Next. This can take a little while depending on how quick your computer is. What it does is it's generating these forward and backward EFA plots. So what these plots are essentially plots of when components are entering or exiting our elution profile for the SEC-SAXS data. So what we've done here is for the forward EFA plot, you take just the first data point, that first scattering profile in your SEC-SAXS data set, and you do SVD. And then you take the first two scattering profiles and do SVD, and then the first three and do SVD, the first four and do SVD, and so on until you've done it on the entire range of the data set. And so what happens at some point, we have a bunch of singular values down constant, nothing's changing, and then when the first component in the data set starts eluting, we have one of the singular values that starts getting stronger, rising up above the baseline. This is corresponding to that first significant scattering component showing up in the data set. We go a little bit further, we see a second component coming up above baseline. This corresponds to the second component starting to elute in our data set. And then finally we see that happen for the third component as well. The backward EFA plot is the same thing except in reverse. We take the last data set and do SVD, the last two data sets and do SVD, the last three data sets and do SVD, and so on until we've done it for the entire data range. And so what this plot is showing is when things are coming back down to baseline, this is when components are leaving our solution. So in this case, with the green line coming back down, that's when the first component exits the solution. Here's where the next component exits the solution, and then the final component exiting the elution that we're measuring. So essentially we can use these forward and backward EFA plots to pick the range of the components in solution. Now RAW tries to automatically guess where these start points are. In some cases it does better than others, but we do need to tweak these to make sure we're right where these components are rising up above baseline or falling back to baseline, which is sometimes a little bit difficult to tell. So what I'm going to do is I'm going to tweak this forward value. You can either type directly into the box here, and then hit enter, or you can use the arrows over here on the side. Since we're close to the values, I'm going to use the arrows just to tweak this down a few points. You can see now we're right at the base for the blue. I'm going to tweak the green up a little bit, this second value. You can see we're right at the base for that. Then I'm going to do the same thing with the backwards components. The first two look pretty okay to me, but the green and the orange look pretty okay to me, but this blue one here needs to come further down, so that didn't quite get it right. Once we're happy with these initial ranges, we'll have a chance to tweak them on the next plot. So once we're happy with the initial ranges, we can just click Next. Again, this might take a little while depending on the speed of your computer. What it's doing is it's carrying out the actual rotation from the evolving factor analysis back into scattering profiles. So on the left here in this top plot, we see the ranges for the different components that we've just defined by picking out the start and end points in the previous plot. And there's an assumption that goes into this, which is essentially just that the first component that starts eluting is the first component to stop eluting. So we match up the leftmost point where a component comes out with the leftmost point where a component exits the data set, and so on. And that creates these ranges here. We then use those ranges as constraints to rotate the singular vectors back into actual scattering profiles, and you see that on the top plot here. These are the scattering profiles for each range. Note that the point of evolving factor analysis is not necessarily to get well-resolved, high-quality scattering profiles for each component in the dataset. Instead, the point of evolving factor analysis is to remove the influence of each component from the other component, so that even if they're overlapping, you get profiles that correspond to just single monodispersed species in solution. Depending on how strong the species is in solution, what the concentration is, how much scattering it has, you may not be able to get a good scattering profile for it, but you can at least remove its influence on the other scattering profiles. So what we're seeing here is we're seeing two very weak components that we likely can't analyze, and then one component that corresponds to the main component in this peak that is something we can actually go ahead and analyze. So we have the scattering profiles on the top. This bottom right plot shows the concentration profiles, what the peaks look like in the elution. These should be ideally reasonably look like elution peaks, otherwise something has probably gone wrong. And the total area is normalized to be constant, so the overall height of the peaks is arbitrary compared between the peaks. The final thing, and perhaps the most important thing we want to look at, is this mean error weighted chi-squared. So what this is taking this deconvolution, transforming it into the kind of data set that we're seeing here in the intensity plot, and then comparing between the deconvolved data set and the original data set, how well do they match? How well does the deconvolution fit the original data? And so what we can see here is that overall it's pretty good. It's more or less flat, but there are a couple places where we see spikes. And so what we're going to do now is we're going to tweak the endpoints of this range to try to eliminate the spikes in this data set. So I'm going to start out with this spike right around 200. It's a little bit below 200. So I'm going to go to my component range controls, and you can see that there's one component that has a range that ends almost at 200. So what I'm going to do is I'm going to try tweaking this range up initially. And you can see as I tweak the range up, that spike goes away. So now that is better. You can see there's a spike somewhere around 300, 320. We have two components that are in that range. So it's not clear which one I want to adjust or which way to adjust it. So I'm going to start with this 321 here and try adjusting that down. You can see as I do that, that component grows. So I'm going to bring that back to 321, and I'm going to try adjusting this bottom range here. I'm going to bring that down initially first. You can see that actually eliminates the spike. This makes sense. There wasn't any overlap between these ranges previously, which meant that there was a little bit of the data set here that just wasn't getting fit properly. So there's a couple other spikes we could try to eliminate. This one right here, it doesn't look like very much, but it's right around 150, 160, and I have components that end around there, so I can probably get rid of that as well. I'm going to try tweaking the start of range 1 down, and you can see that that eliminates that little spike there as well. So now I've got all the components set. We've got the best kind of mean error weighted chi-squared that we think we can get. What I'm going to do is I'm going to click back, and I'm going to verify that changing those component ranges didn't move us too far away from where these components seem to be coming in or out of the data set according to these EFA plots. As you can see, these all still look fine. We're right about where things are coming up or dropping back down to baseline, so we're good to go. The other verification that I want to do is right now we're constraining all the components to have a positive concentration. That's physically a reasonable constraint, but we want to make sure this isn't significantly affecting the data set. So I'm going to try turning these constraints on and off and watching what changes on the concentration plot. And you can see that there's really very little change. For this really weak component, this third weak component, it gets a little bit of a dip here. But for the strong component, there's no change. For the other component, there's really no change, it's just noisier. If I turn off all the constraints at once, again, essentially nothing happens. So in this case, the constraints aren't significantly affecting the data set, which means we probably have a good deconvolution here as well. So we're now happy with the deconvolution. We want to click the Save EFA Data. So this will save things like the chi-squared plot, the concentration ranges, the forward and backward SVD plots. So we can just click Save. I already have a file of that name in the folder. I'm going to overwrite it. Before we finish, I want to note that this method was originally developed not for RAW, and so if you do use this method to analyze your data, please cite the appropriate paper. You can find that by clicking on How to Cite. You can also find it on the RAW website. Once we're done, we click the Done button. that sends all three of those scattering profiles to the profiles plot. You can see them here in the subtracted profiles. And you can see their names. They have the name of the series _0, _1, _2. This corresponds to that first, second, and third component respectively. If you were to right-click and show history, it'll also show you, it keeps track of the fact that this came from EFA, what the component number was, what the component range was, what file name it came from. So that's a useful thing to look at as well. You can see that essentially two of these components are too noisy to get reasonable results from. So I'm going to go ahead and hide them. But we do have one good component that should now be unaffected by any information, any scattering from these other two components, and we can carry out a Guinea fit and molecular weight as usual. So I want to look at one more data set with the EFA, just to show another way of doing it. So I'm going to load up this PSA data set here in the Files tab. This is bovine serum albumin, which is kind of notorious for having both monomer and higher order oligomer eluting at the same time. It's very hard to avoid that. And if you don't use a column that gets baseline resolution, you end up with a very clear shoulder. We can see that in the RG distribution. It goes up, it comes out flat. So this data set here, I'm going to do EFA on. And what I want to show you is that we can actually, in some cases, you can limit the range to make the EFA work better. So for this data set, it looks like there's three components initially. But the more components you add to your EFA, the harder it is to get the EFA to work correctly. So what I'm going to do is I'm going to limit the range, go to about 100. So we're just at the start of the peak. And then I'm going to bring in this end range as well, maybe closer to 250. I'm actually going to bring it back further until I see that third component essentially drop out, somewhere around here. So you can see now it looks like there's really only two strong components in solution. So we are going to lose a little bit of signal to noise when we do this because we're losing part of this peak that we're not using for EFA, but we don't have to try to extract out a third component. And so the benefits of that, making the EFA easier, may be worth it. This is at least something you can try on your data sets. I now need to change the number of significant values from 3 to 2, and then we can go to the EFA plots. So here I'm going to just adjust the forward and backwards starting positions as we'd previously seen. For a component that hasn't come all the way back down to baseline, like you can see here, even though it's a little obscured by the legend, you want to pick all the way to the end of that component as the point where the range ends. When we click Next, you can see the component ranges, you can see the profiles, you can see the concentration profiles. One of them isn't complete. And we have the mean error-weighted chi-squared. So we have a spike around about 185. There's one component that's ending right there. So I'm just going to adjust that up a little bit. And you can see that now looks good. There's another one around 150, so I'm going to adjust that range down a little bit. And you can see that now looks good as well. So now we have a reasonable mean error-weighted chi-squared. We have two scattering profiles, reasonable concentration profiles. So I'm going to go ahead and click Save EFA Data. And then I'm going to click Done. This is going to send the profiles back to the main plot. I'm going to hide the results from the previous deconvolution. And you can see that we now have two components that are actually reasonable that we could analyze. So I right-click, do the Guinea fit. First component, rather large but quite good. The second component actually shows strong signs of repulsion. EFA isn't removing that effect because I guess all the data that we used is repulsive. This means you'd really want to rerun that experiment with either more salt or lower BSA concentration. But if we look at the molecular weights, you can see we have one that's, depending on which method of these is working best, somewhere around 195 to about 220-ish maybe. And we have another one that's about 65. So I know the molecular weight for BSA is about 65, so in this case I would say that _1 component is a monomer, and the _0 component is most likely a trimer, based on the molecular weight. So that's just another way that we can approach the EFA. We don't have to use the whole range of the data set. If you have something very complicated, if you have 4 or 5 things that are eluting, if you can isolate it to just 2 or 3, that can really improve your EFA. The one other thing I want to mention about EFA is, while it can be very powerful, the deconvolution can lead you astray. So my recommendation is always have another way to verify what you're getting out of the data set. A good way of doing this, for example, is doing a SEC-MOLS experiment, or ideally a SEC-SAXS experiment, where you can get accurate molecular weights, ideally for each component of the peak, and verify that the SAXS molecular weights correspond to that, so you know that they're real components in solution. You could also use another deconvolution method to see if you get the same thing, or do something like AUC again to verify the molecular weights. There's a number of ways to do this, but best practice is to verify whatever you get from EFA against something else. With that, that's the end of this tutorial. You should now know how to use evolving factor analysis, or EFA, in RAW to deconvolve overlapping components in SEC-SAXS datasets.